survey. I've been there since 1996 in my official capacity, but I worked with the survey as a postdoc before that. I'm a geologic mapper, geologic map. So we'll talk a little bit about what a geologic map is and what I do as we go along. Since I work in California, one of the applications of geologic maps is the study of earthquakes. So I work a lot with earthquakes, earthquake hazards. California-wide, pretty much, I've lived in California all my life. I was born in Oregon, but moved here when I was 3. And so, no worries, I can't even remember Oregon. Grew up in Northern California, went to Southern California for college, and then came back to Northern California to work. California is pretty much where I've been all my life, so I know a lot about California. If you want to know about the geology of other parts of the country, I may not be the right person. I was going to show you guys something with the computer, but in fact I have my PowerPoint in my talk, but on the way over here I decided not to, partly because we don't have that much time together, and partly because there's a lot of facts and figures. And as interpreters, you guys are likely to be out on the trail or in places where a story would be better than a lot of facts and figures. So I'm going to leave my thumb drive in my pocket, and we'll talk about some stories, Pinnacle stories. Sierra will back me up on this. The story of Pinnacles is written in the rocks. You just have to know how to read the story out of the rocks. I'm a geologist. A geologist is a little bit different from some kinds of scientists. We are much more like detectives because for what we study, everything has already happened. We come on the scene, and everything is done. And we have to look at the clues that have been left to figure out what happened. How did things get the way that they got? The two concepts about geology you guys are going to have to just get your heads wrapped around and talk about geology. One is the idea of geologic time. So let's take 100 years. Let's say we're going to live for 100 years. That's kind of the time that we understand as people. 100 years is a lifetime. A lifetime that most of us don't actually get to. But let's just say 100 years. That's sort of what we know as people. The shortest division of geologic time is 10,000 years. That's the Holocene. That's the geologic period that we're in, the time since the last great glacial advance, the last ice age. 10,000 years, or 100 times a human lifespan. So the smallest amount of geologic time is far greater than anything that we actually experience or think about. And so when you talk about geology, you have to sort of put yourself in a different mindset in terms of time and how much time things take. So we'll talk about things moving and things changing and things growing and things going down and up. And we'll talk about vast distances, hundreds and hundreds of miles, many, many miles deep, and then lifted up many, many miles. And it's hard to, as people, to envision that the Earth can do that. But the Earth can and does do that. It just takes its time because it moves on its own time. The Earth is billions of years old. So if the smallest amount of geologic time is 100 times a human lifetime, the largest amount of geologic time is 10 million times human lifetime. So unimaginably vast amounts of time. You have to sort of put yourself in that time frame. The other thing that we have to sort of think about is that we sort of tend to think of the Earth as this sphere of rock that's spinning around the sun, and that it's solid and kind of homogeneous, same all the way through. And that's absolutely not true. The Earth is mostly solid, but it's not a rock all the way through. It's more like if you took a sphere of steel in the middle, and then you surrounded that with another sphere of melted steel, and then you surrounded that with a much thicker sphere of toothpaste. Solid but gooey. Play-Doh. Even Play-Doh might be too gooey. And then on the very outside, like an eggshell, you've got the solid stuff that we all know about. I'm standing on concrete. I need a rock. But you know, we know what rocks are like, and we think the Earth is supposed to be like that. And so we think, if the Earth is made up of these rocks, how can it move around the way that we're going to be talking about things moving around if it's a rock? But it's the rock that we know is only the very thin little skin on the outside of the Earth. And we think, oh, how can it be a thin little skin? We've got great mountains that go up and great valleys that go down and oceans that are so deep. But the truth is, the Earth is smoother than a cue ball. If you take the roughness of the Earth, we think it's rough because we're tiny, but compared to the size of the Earth. But when you look at the Earth from outer space, you guys have all seen the picture of the Earth from the moon, right? That famous picture. Next time you look at it, notice how very, very smooth the Earth is when it's viewed from far away. It is smoother than a pool ball. And so, the outside of that very smooth Earth where we live is made up of the hard stuff. But because it's just a little eggshell on the outside of all of this this gooey stuff, it can move around on top of the gooey stuff. And it does. It moves around. It's broken up into big plates, they're called. And they move around on the Earth, and they bump into each other. One goes down underneath another, they pull apart from each other, or they grind along next to each other. Because the middle of the Earth is hot and the energy is constantly trying to get out of the Earth, that surface of the Earth is constantly moving around. About how fast does it move, do you say? Well, in human terms, it moves about as fast as your fingernails grow. Not very fast in human terms. Of course, if you let your fingernails grow for 1 million years, they'd be 35 kilometers long, so that's pretty long. And so again, you have to step out of the human idea of time, or the human perception of time, and get into the Earth's perception of time. And something that's moving the rate of a fingernail going is actually moving pretty fast. And so with those concepts in mind, with those ideas in mind, let's talk about some of the stories that the rocks here at Pinnacles can tell us. So this is a geologic map of the Pinnacles, and I told you this is what I do. Let me put it up here so that everybody can see better. Fall down. So how is a geologic map different than other maps? Well, tell me, how is this map different from other maps, like Google Maps? What do you see about this map that you think is different? I see a hand up, but he's a geologist, so I'm going to see.
No, I'm going to say it's more colorful.
It's more colorful. Oh, gee. That's right. It's much more colorful.
It's a different focus.
What's that?
It's a different focus.
It's a different focus. But see, you're interpreting. I asked you what looks different. We get this all the time.
But it's telling you what's going on below the surface.
You will get this when you're out there interpreting. You will say, tell me what you see. And people will start by telling you what they think that it means. Right? It's a different focus. You're right, it is a different focus. But it...
Different subject.
Right. How is it different? How does it look different? He says it's got lots of colors. That's a look. Right? And then I can ask you, what do the colors mean? What do you think the colors mean?
Strata. Different strata.
Different kinds of rock. That's exactly right. Not just kinds of rock, but ages of rock. Because we're going to talk about the story, and in a story you have to know what happened first, what happened second, what happened third, so we keep track of how old the different kinds of rocks are, and what kinds of rocks they are. And that's what the colors mean. That's exactly right.
Can you tell how deep those colors, what they represent? You know, like a thin layer, or a all the whole bedrock is, because of this. I mean, does that tell you?
Yes, but not by the color. You can't tell just by the color. So there's more on here than just the color, and it might be hard to see from back there because the color is really the thing that grabs you as being different. But there are also lines and numbers and symbols on here. And all of that sits on top of a map that describes the shape of the land. And so it's a topographic map. You've hiked, you're familiar with it. It has contours, it shows the shape of the land. And so by looking at the shape of the different kinds of rocks and how they follow or don't follow the shape of the land, you can say something about how they're laying in. So something that's flat follows the shape of the land along, but something that's straight up and down cuts across the land. And so by looking at the geologic map and the shapes of the colors, as opposed on top of the shape of the land, you can tell something about how those are laying in. And by the size of the color, you can tell how thick it is. But you can be fooled because something that's straight up and down can appear thinner than something that's that same thickness that's tilted over, because that kind of spreads it out. You can imagine that if something was, well, think about a mesa. We've all seen a mesa, right? A map of a mesa shows that flat layer covering the whole mesa, right? So that appears the whole area. If you interpreted how thick it was from how much it showed on the map, you'd say, wow, that's really thick. But it could be quite thin. You're just looking at the flat side of it.
Does this color represent layering? Like, for example, like the brown could represent, you have one that's here on top, but another one underneath, throughout that whole area right there.
Well, we'll talk. So that each color represents a kind of rock.
Okay, specific.
Kind of rock and a certain age. And some of them have layers, and some don't. And so the colors don't really tell you whether they're layered or whether they're not. They tell you what the rock is and how old it is. And there's a key that goes along with it, right? So you match the color to the key. And there are labels here that help, as they tell a little bit. The label, each color has its own label. So this pink color is labeled KGR, and that helps me remember what kind of rock that is as a geologic map reader, so I don't have to constantly go back and forth to the table. So, we're going to be talking about the story system. So I've got a map here that shows where all the different kinds of rocks are. And we're here by Shalom Creek Campground, actually right here where the old campground used to be. And the green line that you can't see because it's too faint, but it kind of goes around here. So this is Pinnacles National Park. The last thing I want you to notice, if you can, is that there are lines on here of different thickness and different colors. And just like a regular map, right, where a freeway might be a line of one type and a country road might be a line of another type, these lines show different things. The thick lines and the red and orange colored lines, those are the faults. Faults are places where rocks of different types have been moved. Remember we talked about how things move. Well, when they move next to each other, they move along a crack in the earth called a fault. All a fault is a place where the rock on one side has moved next to the rock on the other side. It can move sideways, it can move up and down. One can slide over on top of the other, one can be pushed down below the other, they can slide the other way. A fault is just a place where things have moved or are moving. Right? Not all faults are still moving. Right? So there are a lot of faults on this map. Not all of them are moving. There's one famous fault that is still moving.
Yeah.
This one.
Yeah.
Right there. It's the San Andreas Fault, which you may have heard of. And it's still moving. We're here on top of, right on top of this orange line, the Shalom Creek Fault. And we'll talk about the story of the Shalom Creek Fault. It is right here. And the Pinnacles Fault is the other big fault that will come into our story. So three faults to play a big part in the story of Pinnacles. Okay, let's start with some stories. Why don't we start with the story of the oldest rocks in the world? Right? The volcanic rocks, I should say, are what everybody thinks about when they think Pinnacles, but there's a much, much older story than that. There are little tiny bits of rocks over here on the west side. And those, to start the story of those rocks, you have to go back to the time before the time of the dinosaurs. Did you know there was a time before the time of the dinosaurs? Yes. There was, of course, a time before the time of the dinosaurs, and you go back 250 million years, and the rock, or what was to become the oldest rocks in Pinnacles, were deposited. They were deposited in tropical, shallow ocean waters, sand, and coral reefs to make up layers of sandstone and limestone 250 million years ago, and far south of where we are now. That wasn't hard because North America was farther south than where it is. So everything was farther south, and to get into the tropics was easy. Southern California was near the equator then. So the rocks those oldest rocks were there near the equator, near Southern California, 250 million years. Sandstone and limestone, maybe a tropical island beach, nothing like the desert that we have here now. Built up layers of sandstone and limestone that were eventually scraped off and added to the western margin of North America and buried deep in that eggshell, 5 miles deep. And you can imagine that if you're under 5 miles of rock, you're going to get a little bit squished and a little bit cooked. And so what started out as sand, and coral, and lime, crushed and cooked and turned into marble and quartzite. And we still have bits of that in Pinnacles today. If you walk west of the new visitor center and the new development over there, there's a road that goes up to the top of the hill. I think there's a water tower up there. On the left side as you walk up, you see some white, sort of conspicuous white rocks. Those are the marble, the quartzite, that originally started its story before the time of Columbus.
And Russ, where exactly are those white rocks?
If you walk up the road towards the water tower, as you go around the curve, look at the road cut on the left side.
Which road are you on? Which water? I'm trying to get this actual placement.
Well, I'm not sure I can describe it better than that without actually going there. There's really, I think there's only one road that goes up one hill west of the barracks on the west side.
So if you're on the west side, on the west side,
On the west side.
and there's going to be they cut a road to get everything for the drip system over there, so it's a big scar.
Yeah, there's a big road cut on the left side of the road as you're going up, and as you're going around the curve, look for those rocks.
So these rocks deposited when you just had a passive plate boundary here, or is it still? I can't remember the big picture history.
There was subduction and accretion in Western North America at that time, but it was sort of a quiet system, mostly quartz sand and reefs. So not anything like what we have off coastal California today with cliffs and lots of bits of rock, lithic sands.
Yeah.
And no coral whatsoever. So that's the story of the very oldest rock. And those are just little iffy bits and pieces scattered around on the west side. If you look at the map of the west side, you'll see that it's mostly this pink rock that we're talking about.
So you said the green part is the quartz?
No, the quartzite and the marble are so tiny that they only show up as these little purple dots, and they're mostly outside the park.
Oh, okay, purple dots.
Purple dots here. And the ones inside the park are so small they're not even but they're here. And so if somebody asks you, where does the story of Pinnacles geology begin? You can say, let me take you back to the time before the time of the dinosaurs. That's where it begins.
Now, is that when Pangea was, when everything was all together?
Everything was together and everything was farther south.
And when did all that split apart?
We'll fast
You'll get there.
We'll
Okay,
get there.
okay.
So let's talk about the story of the next one. Let's go to 100 million years ago. Our marbles and our quartzites are deep in the earth in Southern California, where the Mojave Desert is. So you've got 5 miles of rock on top of you, your marble and quartzite. You've been sitting there now for about, it's been 150 million years since you were laid down in the ocean. Kind of bummed because you went from a tropical beach and now you're crushed by 5 miles of rock on you. But you're sitting there minding your own business, and something on the margin of North America changes, and all of a sudden a lot of magma starts to filter up into the area there, all along the eastern side of California. Magma, melted rock. This magma full of silica, and potassium, and sodium, and the material that will eventually solidify to form a rock called granite. You all know what granite looks like. through the cracks in the rock, this melted material comes up and it melts the surrounding rock, and carries away pieces of the surrounding rock, and it forms big, I want to say spherical, but more like balloon shapes of molten rock underneath eastern California. And that magma feeds up through pipes into giant volcanoes, sort of like the Cascade volcano. Mount Rainier, Mount Hood, Mount Shasta, Mount Lassen. We had volcanoes like those all along eastern California 100 million years ago, but down below their plumbing, there were these big chambers of magma. And over the millions of years, those grew next to each other, overlapped on top of one another, melted each other, until you had what's called a batholith, or gigantic mass of rock that formed from this magma, this granite rock. Now, the one thing about granite rock that you'll notice, we'll see some as cobbles, and we'll stop and we'll take a look at it. The one thing you'll notice is that it has big crystals that are all interlocking together. And that's an indication of how granite forms. By slowly cooling over thousands and tens of thousands of years, these crystals have lots of time to grow. And they grow nice, beautiful crystals until they bump into one another, and they grow around each other until they're all locked together. And so there's no void space in the granite. There's no porosity. If you were to sink a oil well into a granite, you'd be wasting your time, because there's no room for oil, right? The oil is in the spaces in rocks. In granite, there is no space. And so 100 million years ago, we have this these great granite bodies form and cool and solidify deep under the earth. How do they get up to where we can see it? Right? We've got two kinds of rock now, 100 million years ago, the marble and quartzite, and the granite, 5 miles deep in the earth. But they're not 5 miles deep in the earth. We walk around on them now. So how does that happen?
Can I ask a quick question?
Yeah, absolutely.
How does it cool when it's 5 miles deep into the earth?
Oh, it's a good question. That's an excellent question. It cools because 5 miles deep in the earth is normally not hot enough to have melted rock. So melted, you can imagine, melted rock has to be really, really hot. So when we put our limestones and our marbles down there, they didn't melt. They got crushed and baked. They didn't melt. So it's normally not hot enough, even 5 miles down, to have melted rock.
How many miles to the center of the earth?
I know that off the top of my head, but I never do. The earth is about 24,000 miles around, and so it's about 8,000 miles across to about 4,000 miles to the center of the earth. Roughly. Very, very roughly. Pi was equal to 3 there, and all kinds of approximations, but that gives a rough idea.
So yeah, 5,000. 5 miles is
5 miles is a tiny little bit.
Yeah.
Remember, you're still in your eggshell, right? You're still in that little crust around the Great Big Earth, where the mountains that we think are so amazing are not enough to make us any rougher than a pool.
Yeah, our park geologist at Yosemite, when I was training there, told us it took the better part of 1 million years to go from magma to solid too.
Because it is very
rockiness
hot,
there.
and so it cools very
Yeah.
slowly. And that slow cooling is what allows the big crystals to grow and lock into each other. When we talk about the volcanic rocks, where the magma comes out onto the surface and cools much more quickly, we'll talk about what rocks cool quickly from magma. But first we have to get our granite to the surface because the volcanic rocks sit on the granite. So, 100 million years ago, time of the dinosaurs, let's fast forward to about the end of the time of the dinosaurs. And close to the end of the time of the dinosaurs, something very funny happens in Southern California. The batholith breaks into two. The Sierra Nevada part of it stays where it is, and the part that used to be where the Mojave Desert is now starts to move. And it moves west, and moves south, and it continues to move until it comes up and over and buries the surface all the way out. I think all the way out to the coastal range, at least. It comes across the Great Valley, it comes out, and it comes over. And it takes millions of years to do that, tens of millions of years to do that, until the rocks that used to be in eastern California are now in western California. And these granitic rocks, not only do they move west, a little bit south, they also get pushed up. As they come up and out and over to the surface. And they get stuff that used to be on top of them, it's eroded away. And it's totally gone. The rock where the granite comes up and out and over is this rock here. It's called the schist of Sierra de Salinas. About 75 million years ago. This was sandstone, sitting in the Great Valley. Well, the southern Great Valley that isn't there anymore because this stuff got stacked on top of that. Now this doesn't quite reach the park. The edge of the park goes right here. So it's not in the park at the surface. You can't take people to see it in the park. But when you drive up the road from the west side, you go right through it when you're here in Shirt Tail Gulch. And this stuff probably goes all the way underneath Pinnacles, all the way to Shalom Peak. So it's here, but it's still down there.
Got some großen Scheist.
There's lots of schist underneath the Pinnacles. So that's how we get our granite to the surface. Now we don't have any rocks that are younger than the schist, but older than the volcanics. So we have a gap in our story. We have to sort of fast forward from about 70 million years ago to about 23 million years ago. So 23 million years ago, about a mostly granitic plain in western California. It's pretty near sea level, we think. And once again, we have a change at the edge of North America, where the rocks of the ocean used to be pushed under North America along its west edge. We have a change now, and things start to go sideways. Instead of going under, now the two plates are moving next to each other. But the plate that was going under keeps going down. And that opens up a gap, and heat and material from below come up, and they start to melt in places. The crustal rocks here, the rocks here. And that melted rock comes up to the surface, and it erupts as a volcanic field. What's a volcanic field, you say? Well, don't think of the source of the Pinnacles as one big, giant volcano. It probably was never one big volcano. We know that by a couple lines of reasoning, and we can talk about that as we walk later if you want. But for now, we're going to talk about this as a volcanic field. A volcanic field is an area with lots of little volcanoes. So Pinnacles is almost definitely the result of lots of little volcanoes that erupted for 1 million years, 1.5 million years, in an area that was slowly going down, and it allowed a thick, very thick, by human standards, right, but by the Earth standards of thin little scum, of layers of volcanic rock. The other thing to think about the Pinnacles, and we'll see some layers as we go, these layers of volcanic rock were probably laid down close to flats. We know that because within the layers we have one layer that is an ash that got erupted and fell into water, probably a lake. And we know that because it has little tiny fossils in it called ostracods. And when ash falls into a lake, it makes a horizontal layer, not a tilted layer. Right? You think about lava flowing down a volcano, and you want to think about it as forming a tilted lava flow. But the ash layer from the lake is tilted the same amount as all the other layers. So most of these layers were originally pretty much flat. All the tilt you see has happened since then. So imagine, if you will, now a 7,000 feet thick stack of these volcanic layers that are mostly flat. And then they get cut in half. And the west side starts to move north, and the east side stays where it is in Southern California near the mountains. And that's the story that you probably already know, right? The story of how the Pinnacles is one half of the Pinnacles Nenach volcanics, and they've been moved apart by almost 200 miles since they were formed about 22 years ago.
So they're formed or just split?
The volcanic field formed about 22 million years ago. We don't know exactly when the split happened and Pinnacles started to move north. Clearly after 23. We think that most of that movement has happened in the last 6 million years. So it started slowly and then later spread. And that story, which most people don't know, and it's the story that actually brought me to Pinnacles, part of my job. That's the story of these brown and tan rocks over here on the other side, and the story of the Shalom Creek and the Pinnacles zone. You've heard that Pinnacles has moved north on the San Andreas. And that is almost true. It has been moved north by the San Andreas Fault, but not just the San Andreas Fault, because the San Andreas Fault isn't a durable fault. It has, throughout its history, it moves around. Sometimes it's favorable for it to, well, right now it's favorable for it to be here. But about 2 million years ago, it was over here, what we call the Bear Valley Fault. So if you're out in Bear Valley, you go forward, leave the park and turn left and head toward Hollister. Right? And you look at the hills on your right. The Bear Valley Fault goes right. The old San Andreas Fault 2 million years ago is right there. Halfway up those hills, there's a big change in the kind of rock. So the rocks that we have here at Pinnacles, they end about halfway up those hills east of Bear Valley. And the rocks on the other side they belong to North America. They belong to the North Americas. They belong to that side. The San Andreas Fault isn't the boundary between the rocks that moved and the other rocks. The Bear Valley Fault is that boundary. Within the park, though, we've got these two faults, and you'll notice that the Pinnacles, volcanics that we all know and love, are trapped between these two faults. So why is that? Why is, if the San Andreas Fault, or even the Bear Valley Fault were the fault that moved them, why don't they go all the way over there? The answer is because these faults have moved them too. So what about the story of those faults? Well, the story of those faults starts about 14 million years ago. The San Andreas Fault was actually over here. The Shalom Creek Fault and the Pinnacles Fault were the San Andreas. Came up and they took a bend to the right. And because they had that bend in, think about it. Here's my there's my fault. It's bent to the right. And now I'm going to slide it along. Right? North, the Pacific side here is going to go north. Pinnacles is right here at the base of my thumb. And it's going to slide along like that. And what happens when it slides along is it pulls apart. And that's exactly what happened. And we know that because these rocks here record that. This is where that basin, that pull apart was formed. These rocks stayed high. These rocks, the rocks on this side went down, and material, big boulders from here were eroded and washed into here and redeposited. So huge landslides rushed down from this uplifted area here and filled up the hole that was opening up here. And between the landslides, there were periods of quiet. And in the periods of quiet, the water was home to plankton. And those plankton lived their lives and they died and they fell down. So in between the deposits from the huge landslides, there are these layers that are mostly plankton, kind of plankton called the diatom. That's how we know how old or when this story is, because diatoms don't live for very long and they change. Not in human time scale, but in geologic time scale they change. And so we know that the oldest diatoms are over here, and they get younger as they go this way. And so between about 14 or so million years and about 8 million years, this was high, this was low, there was salt water here, and boulders and material washed across and filled in here. Lots of layers. We'll look at some of those layers. And the lucky thing for us here at Pinnacles is that we had two faults. Because if there was just one fault, all of this would have been lifted way up and eroded away, and there wouldn't be any pinnacles here, no volcanic layers left. It would all look like it looks over here on the very west side of the park and west of the park. These long, skinny purple lines and green lines, that's the plumbing from the volcanic field. The part of the volcanic field that was over here. So this Pinnacles used to go all the way over here. But this part got lifted up and all the volcanic rocks got eroded away. All the volcanic layers that were here are now boulders and pebbles and cobbles and sand here. but because there were two faults and not just one, there was an in-between block that got lifted up some, but not too much. And so while this got eroded away down to the granite, in between, some was preserved. It's tilted. You can see that the granite that was once underneath all of these layers is showing over here. So the whole thing tilted this way. But this stayed low enough, the material washed across it. And those tilted layers, even though they were beveled off on their edge, were preserved. So it's a good thing that we have two faults and not just one. And that story continued until about 8 million years ago. And then this bend, for what the San Andreas Fault didn't like that bend anymore. Maybe it was too bent. Maybe it was easier to go a different way. So it started to abandon this. The pulling apart stopped, and those layers of sediments that have been laid down here, they were crunched and folded and tilted themselves and eroded off on their edge. And a younger layer was put on top of it. And you'll notice that there's no change in color because this is an old map. One of the things that we're doing right now is we're mapping out the edge between the younger brown stuff, if you will, and the older brown stuff. So eventually this dark brown will be broken up into two different colors. Because now we know that there's an old and a younger part. That younger part that we call the Cave Canyon member. So there's the Shalom Creek member, that's the older one that's more tilted. And then the Cave Canyon member, that's the younger one, and it's just gently formed. They probably formed between 8 and 6 million years. And then, by then, this system had pretty much, this valley was all filled up, this system had died out. All the slip on the fault was over on the east side now. And another layer was put on top, and that layer wraps all the way around, and it's about 5.5 million years old. And that's this one. It's labeled, it's called the Concha Rico Formation. Concha Rico Valley, which is down south of here. And it goes across all these faults, so we know that those faults were mostly dead by about 6 million years. So the San Andreas Fault was over here from about 14 or so million years ago to about 6 million years ago. But now it's not. So remember, I told you that faults are where things have moved. They're not all moving anymore. The Shalom Creek and the Pinnacles faults moved a lot. They were part of the story. We think that these rocks here moved at least, so we're going to throw kilometers on you, at least about 40 miles relative to these rocks in here. That's because of how long that pull apart valley was. At least 40. But now they're totally dead.
So you're saying that the San Andreas Fault shifted from the Bear Valley Fault, the Shalom Fault, Valley Fault into its present?
So it kind of depends on where you're sitting, but if you were, say, sitting in the West Side Visitors Center here, 14 million years ago, the San Andreas Fault would come down here, bend, and it would occupy these two faults here. So you would, if we lived here 14 million years ago, it would be the San Andreas Faults, plural. And you would say that the main active fault was this fault, the Shalom Creek Fault, but there was also this other fault, the Pinnacles Fault, and those would be the San Andreas Fault. Until about 8 million years ago, when these faults started to die off, and another fault would be over here, so you'd say, okay, now we have 3 faults going, and then about 6 million years ago, these faults are totally dead, and all the slip is over there, but not on the San Andreas Fault, or not entirely on the San Andreas Fault, but also the Bear Valley Fault, until about 2 million years ago, when the Bear Valley Fault, for the most part, gives up the ghost, and now the San Andreas Fault is the San Andreas Fault.
So why is it still called the San Andreas Fault when it's in another location? Why not just rename it?
Well,
Or what? I guess what defines a fault?
right. So when I say that the San Andreas Fault was over here, what I really mean isn't that. You're right. This is the San Andreas Fault, and the only fault that should be called the San Andreas Fault is this one. But we think about, right? We tell people. So you're right. Technically, there's only one San Andreas Fault. As geologists, we talk about the San Andreas Fault system that includes all of them, and many, many more.
Yeah, so there's a geographical area south of here, like 200 miles. And somehow that illustrates the same thing that's going on here.
Okay, so you're sort of asking, how do we know, right? You'll see there's lots of different colors here, and they're in a certain order. That reflects a tilted stack of volcanic layers that formed about 23 million years ago. That stack has a certain order, and about 200 miles south of here, on the other side of the fault system, there's another stack of volcanic rocks, 23 million years old, same kinds of rocks, stacked in the same order. A geologist named Vince Matthews noticed that there were these 2 stacks of the rocks that were the same age, same rocks, in the same order. And he said, wow, 7, 8 layers, I forget just how many layers correlated across, in the same order, the same kind of rocks at the same age. That's too similar to be a coincidence. Those 2 stacks must have once been together as one stack, cut apart, moved apart.
So it's the same DNA, so to speak, but it illustrates the movement.
That's right, because that volcanic field, we know, was maybe 30 miles across, give or take. And now one half is 200 miles away from the other half.
Right.
So it wasn't one giant volcanic field that reached salt, but one smaller thing that's been cut in half and moved. And the importance of that was back in those days, a lot of geologists didn't believe that things could move that far. We didn't have the idea of the plates on the outside that were broken and could move around. 100 years ago, we thought, we looked at the shape of the continents and some other geologic evidence, and we thought, these things look like they could fit back together. So we had the idea of continental drift.
Right.
Until a smart guy came along and said, the continents are made of rock that's softer than the ocean floor is made of. So you're telling me that the continents can push their way through this hard ocean floor and drift around. There's no way that'll work. And they were right. The continents don't float around independently. So we were kind of stuck. So for half a century, we had this observation that things look like they should fit back together, but no mechanism to move them around. Until World War II, we were very interested in finding submarines, especially in the Atlantic. Submarines are made of metal, so what we did was we flew sensitive magnetic sensors back and forth across the ocean, looking for enemy submarines. And one of the things that we noticed was that there was a signal, we could see all the ships and submarines, but behind that signal, that short wavelength signal, there was a long wavelength signal coming from the ocean floor. And geologists realized that that was a record of the magnetic properties on the ocean floor. And when you took and you made a map of the magnetic property of the ocean floor, it was striped and symmetrical across the ridge that we knew about in the center of the Atlantic, the mid-Atlantic ridge. And we knew that that mid-Atlantic ridge had volcanoes in it, and so we realized over a long time that what was happening there was that new ocean crust was forming and moving apart symmetrically on either side of the ridge. And so the Atlantic Ocean itself, the ocean crust, was moving. The continents don't drift, they just go along for a ride with the ocean crust that really drives the whole thing. The continents are just, in terms of plate tectonics, they're just these ice cubes that float along.
So I have a question. Maybe the visitors, when we're talking about geology talks out there, they always ask the same questions all the time. They want to know how wide was the volcanic, well at that time, the volcano,
Right.
but now the volcanic field.
Right.
They want to know how high, elevation was it.
Right.
They want to know how many vents, and they want to know where those vents are. That's what they always ask.
Okay.
So we used to have an old picture here, black and white photo that actually had some areas labeled as vents, like Morshalone.
Right. There are some vent areas that are preserved in the stack. So let's start with the answer. I have some answers and some not. Based on the distribution, not just of the volcanic layers, but also the plumbing, right? The Pinnacles Nenach field is probably about tens of miles, maybe say 50 miles across.
50 miles.
Give or take. That's just a ballpark estimate, of course, right? This is all eroded away. This is tilted on its side. There's a big hole in the middle, and the other half has its own story, right? So we probably don't see all of it over there either. So ballpark, 50 miles across. Lots of vents. A few preserved in the layers here, but an unknown number of vents over here. So all we see are, all of these are called dikes. These are places where magma is coming up through cracks and feeding into the volcanic system. So if there are a bunch of vents over here, you can imagine there were just as many, if not more, over here. Totally gone now.
Yeah, the old literature said there were 7 vents. So obviously
7 vents right here, preserved in the layers, perhaps.
Okay.
Other vents, perhaps, that would have been preserved in the layers but aren't now. Remember that this is tilted and that its root is exposed here. So these layers project up into the air. So a lot of what's here at Pinnacles, or even the part of what was between, right, the preserved part, was eroded away. So maybe more vents. So originally, a lot more vents than the few that were preserved. How high was the volcano? The stack is 7,000 feet thick, but we don't have a 7,000, probably didn't have a 7,000 foot high volcano. What we probably had was a valley that was slowly going down, filling up with layers of volcanic rock until there were 7,000 feet or more of layers. And in that valley, there were all these volcanic vents.
So the layers have built up to, you said roughly
So it's 7,000 feet of layers, but not a 7,000 foot high volcano.
How long do we think it was active? How many, like, it was dated at 23 million years?
Yeah, the radiometric ages aren't very precise. Probably extended for several million years. If you look at all the different ages they've gotten from the volcanic rocks, they sort of span that a few million years. The big uncertainty. So it could be more. Could have all happened in a big rush. We don't know. They all overlap, but if you sort of look at the span of them, it gives you a few million years to play with. We also, the that system of opening up a window as the old slab went down and then the new slab started to grind along, that didn't stay at Pinnacles. That opening slowly moved northward. So we have a series of similar volcanoes that move north. The one that is presently or most recently active is at Clear Lake, north of the San Francisco Bay region, like Canocti Resort. There are recently active volcanoes there. And so some of what we think we know about Pinnacles comes from observing the same thing happening now up there. East of Hollister, Quien Sabe, I don't know. Some of you know that area. If you drive, as you go through Tres Pinos, there's a Quien Sabe road that goes off to the right, just after the Catholic Church, but before most of the town. Over there, that's where the volcanoes were 12 million years ago. Not all, some of them, but most of them, yeah. Antimony Peak, off to the east there. The Berkeley Hills have the volcanics from about 8.5 to 10 million years ago.
So, going back to the vents that are preserved, do you know, I mean, I was told that it was like North Shalom, that it was,
I don't know exactly how many or where they are. Okay. I haven't studied volcanic layers in detail. The volcanic layers themselves were studied in detail by Professor Matthews. So
I think we have his literature in our library.
Yes. It was his doctoral thesis, and then he wrote a number of articles later about. He's been here to talk about that. But yes, the best answer is a few are preserved, but most are gone, and that will let you talk about how the layers have been tilted and eroded around. People want to look at the Pinnacles and say, okay, where are the volcanic features here at the Pinnacles? There are none. All of the landforms you see here at Pinnacles are from erosion of those tilted layers.
Yeah, they keep asking, where's the pointy part of the volcano?
That's right.
They always ask us.
And the answer is that to see the pointy part, you'd have to tilt yourself over about 45 degrees. And then you would have to move yourself back through time about 20 million years. And then the original volcanic landforms might still be preserved. But remember, 14 million years ago, the whole thing started tilting and moving and eroding, and so those pointy peaks are now broken into a million cobbles and pebbles and boulders, and they make up the sand and the gravel of this unit over here. This is called the Arcos of Bickmore Canyon. Okay. It's got two members, the Shalom Creek member, the older one, and the Cave Canyon member.
Relatively speaking, how do you think geology is fairly complex, or not so much?
It's complex in that it has a history. It's got lots of different phases stacked one on top of the other. So if you go to other places, you might, if you just go over east of the San Andreas, you'll get into some rocks called Franciscan rocks. And those rocks are complex because of their history. Those are the rocks that came and got scraped off at the edge of the continent into the subduction zone and churned up and sliced together and brought back up and moved around. And so they're just a mess. So that geology is really complex. But that story is pretty compact, right? I just told the whole thing. There you go. I can tell you how old they are and we'd be done, right? Pinnacles has more stories than that. So the geology here is pretty simple. We've got got a few bits of metamorphic, old metamorphic rocks, those are those marbles and quartzites, a lot of granite, layers of volcanic sitting on top that are tilted and eroded into the beautiful landforms, fault and sandstone conglomerate over here on this side with the diatomite plankton layer.
People always ask me too, another thing I always ask is, we have in our visitors center pictures of the other area, the 190 miles,
Right.
they always say, well, why is it all gentle rolling hillsides and Pinnacle still has these spires and crags?
Right.
And what I've read, it was because of the natural force of erosion is acting more quickly down south than it is up here, or does it have to do with the western hill that we have there?
I think probably all of the above. Also, Pinnacles has a series of fractures that aren't faults called joints. So the layers go this way and there are a bunch of fractures that cut across, and those two planes intersect so that you have a natural way to make a three-dimensional column.
Oh,
You get several of these and several of these, and you can get the columns and pinnacles. I think we've been inside enough, don't you? It's hot in here. Maybe it's because I'm up and moving.